Hello, my name is Vladimir Khomutov, and I work as a core developer for Nginx, now F5, for about 7 years already. And today we are going to talk a bit about running multiple Nginx instances in a cluster, and particularly about, we'll look in depth at a relatively new feature of Nginx-Plus, a zone synchronization module. But before we start with this clustering details, let's discuss a bit typical setup, problems, and our goals. Here we see a typical installation with Nginx as a load balancer and a cluster of backends behind it. And today we're going to discuss quite a different scheme where you have multiple Nginx instances with same backends behind them, feeding them with traffic. But first, why do we want to run multiple instances of load balancers at all? There can be some reasons, and first idea that comes to mind is that we'd like to have fault tolerance. We want to continue to provide our service even if one of our servers is dead. Usually this is solved with some active-passive scheme, and another reason can be the nature of your system. And a good example here would be a content delivery network, where you have multiple edge servers all over the world, and all of them are entry points to your region servers. And last but not least is the will to scale. You want to add more servers and process more traffic accordingly. What makes clustering hard? The state. All your servers have some state, and this state needs to be shared in network. If your systems have no state, clustering for you is very easy. You just add more machines and you have no problems. But of course, in reality, they have state. Let's take a step backward from cluster and take a look into a single Nginx instance. We know that Nginx is a multi-process application, and internally it runs multiple worker processes that deal with clients. And we know that at this state, workers know how to share the state. So let's look what state we have on load balancer and how is it shared. First, the obvious thing, the configuration is shared among all worker processes. Because all workers, they get their configuration from a master process during fork system call. But this state is not very interesting because it is actually read-only. We don't change configuration in runtime, and if we want to change a configuration, we perform a reconfiguration. This basically means we run new worker processes that run with new configuration. So what we are interested in is a runtime state that changes during work. What we have on load balancer. We have different limits, connection limits, request limits, and these are basically just counters like you want to limit some of your clients to, say, 5 requests per second, and you need to account this data. And it doesn't matter which worker process serving this client. It should always work. Also, we have proxy cache metadata. What items are stored, where they are stored, what is their expiration time, and so on. Upstream servers have their own status. Number of open connections to upstream servers, number of failures, and different statistics. We have SSL sessions cache, so clients do not need to perform full TLS handshake each time when they return to our systems. We have number of counters in stop status model. And we have even more in Nginx Plus. In Nginx Plus, you can have dynamically configured upstream servers where servers can be obtained, for example, from DNS, and they can change in runtime. Health checks have their own status for upstreams, and we maintain a, for example, sticky sessions model. And there is a lot of metrics in API model that are shared. We also have a key value store model that again shares its data. And we have some other models like HTTP session log data. So each process may use and update this data. How is this implemented? Nginx uses shared memory approach. And one of its properties is that it requires explicit configuration. If you look into your nginx.conf file, you may find some directives that refer some kind of zone, and it is usually equipped with memory size in megabytes. So you have to explicitly specify that you want to share some amount of memory with other processes. What can we say also about this approach? The access to data is effective because it is just memory. You read from it, you write to it. There is no some complex protocols. You don't need to copy data. You access it in place. So the data is always consistent because typically worker processes, they acquire a lock before accessing this data and release a lock after they are done. So you always know that your data is up to date. There is one consequence. For example, if your process crashes during an update, the data may be left in an inconsistent state. In this case, all you can do is basically to restart your whole Nginx instance. But hopefully this event is quite rare. So the question is, can we just extend this shared memory approach to the network, to the clustering? And the short answer is no. Why is it so? The consistent access to data is expensive, both in terms of code complexity and performance. The scaling will be killed because each node must interact with some other nodes. It can be some master node, subset of nodes, or maybe even all the nodes to provide the response. This doesn't scale. There are protocols that aim to provide strong consistency in a network, but the problem is they're very complex. It's very hard to write properly some such protocol, to implement it, and there are a few people who can actually configure it and use it. Another reason is that network nodes are ephemeral, especially with the rise of containers and virtualization. You start new nodes, very often they can disappear at any moment, and host unreachable is much more frequent event than a crashing process. So chances to fail are higher. And even if we take this path, the result would be a distributed database or some kind of supercomputer. And we're not talking here about supercomputers, it's totally different matter. We are interested in commodity hardware. And Nginx, it is not a distributed database and it's not going to become one. If you really need in your project a distributed database, you better stick to some project that tries to implement it and somehow integrate it into your Nginx. So, what do we want from Nginx in a clustered environment? We'd like to process input on each node separately, without consulting other nodes. We'd like to inform other nodes about changes that we made locally. And we'd like to process new requests, new input with this new data. Can we actually implement something useful given these requirements? There are three strategies we can do. First, we can perform configuration updates. It is possible to update configuration on one node and it will be distributed to cluster. We can perform session caching. When a client starts a session on one node, we share this session with other nodes, and when client will return, it will resume his session on other node. And we can also apply resource limited. We account some client on one node, we share this knowledge with other nodes, and when a client comes to our cluster from other node, we can impose the limit properly. So, according to the strategies, we offering some modulus in Nginx+. In R15, we introduced sticky session synchronization model. In R16, we added key value store synchronization and also distributed request rate limiting. So, the R15 came with Nginx Zone Sync module that implements synchronization engine. It is capable of synchronizing shared memory zones to cluster nodes. And here I've put some main properties. This is a TCP-based stream model. It uses Nginx stream subsystem to communicate over network, and it uses reliable TCP transport. It uses native Nginx asynchronous input-output. So communicating with other nodes is just like communicating with one more client. There is nothing special about it. From a topology point of view, it is a full mesh. All nodes connect to each other. And cluster nodes can be discovered by the means of DNS. To push the data between nodes, we use simple protocol with minimal overhead. It's really lightweight. And we provide full TLS support, so your communication between nodes is secure. And here is a very basic scheme of moving parts in our setup. We'd like to have a cluster of two nodes, Nginx number 1 and Nginx number 2. And in these nodes, we have some HTTP modules that working with zones foo and bar. And we add a stream module, a stream subsystem in Nginx that zone sync model operates in. It knows about zones that it needs to synchronize, and it communicates with same model on another node. Let's look at a configuration, and we'll take as example sticky sessions. Here is a very basic Nginx configuration as a load balancer when it passes all requests from clients to upstream named backend. And backend is simple, it's a couple of servers, and there is a sticky learn directive that uses zone Z to store sticky sessions. So when a client comes, the load balancer remembers which upstream server it used and saves it to a shared memory. Now we want to make this configuration cluster aware. What we need to do? First, we define a stream block, and we define a server listening on some port there. And this address will be used to accept connections from other nodes. So far, there is nothing about cluster yet. It is simple Nginx configuration of a stream block. Next, we add a zone sync directive. And this makes it handle this address in this server. What we do to do next is to describe our cluster nodes. Here we do it statically by just providing IP addresses and ports of other nodes, including ourselves. And finally, we need to mark a zone with a sync flag to say that it needs to be synchronized. And that's all. We can run two Nginx nodes, and they will synchronize contents of a shared memory zone. Of course, configuring clusters statically is not very convenient. And we'd like to use a DNS, and here is a scheme of such setup. When we have a special name, cluster example.com, and it resolves to 3 IP addresses. And each IP address is an address of some Nginx node. What we need to do in our setup to make it use DNS. We remove these lines that statically list our known nodes and replace them with a single line that refers cluster example.com domain name and mark it with a resolve flag. So now Nginx will use a resolver specified by a resolver directive to query a name server for IP addresses of other clusters, of other nodes. And that's all. You can add more records to DNS, and your running nodes will know about other nodes. Again, in real life, your nodes may reside in non-trusted network, typically some public cloud like AWS or whatever. So to secure connections between your nodes, on a server side, you simply add SSL flag to listen directive, you provide certificates, and actually this is basic Nginx functionality that is not related to cluster. You just configure a server-side SSL. And on the client side, you have a bunch of zone sync SSL directives that are actually similar to proxy SSL directives. This is a client-side SSL in Nginx. So everything Nginx knows about SSL, like client certificates, different checks, and everything that it has, it is available in communications between nodes. So we also have other models that support it, and here are examples. It's very simple. The stream part stays the same, and you only need to provide a sync flag to the directives that support it. Currently, it's key value storage and HTTP request limit model. Now, a bit about internals. So each model stores its data as a set of records, organized as convenient to the modeler. We actually don't care. And this is the data that we want to synchronize. So records are opaque for the zone synchronization model. It deals only with a queue of them and has access to methods that serialize that data. The queue contains records that need to be sent to the cluster, and the zone synchronization model polls the output of queues of configured zones at constant interval. And only records created locally on a node may appear in the output queue. And the model consumes the output queue and puts the serialized records into output buffer. And finally, the output buffer is then sent to all currently connected nodes. Here are some configuration details that you may fine-tune the things. The most important one is actually the synchronization interval. It controls update frequency and thus controls how large the inconsistency window of the cluster is. Higher values can accumulate changes at a price of increasing latency, and lower values will decrease latency, but will more frequently maybe lock shared memory zone and increase number of packets sent to network. By default, updates are polled once per second. It may or may not suit your needs, and the optimal value will depend on the nature of your system and needs to be found experimentally. You can also specify zone sync buffers directive, and this will control how much data will be read from shared memory, how much memory you will use for synchronization. Smaller buffers will probably save more memory, but will require, again, more lock-in to access shared memory zone. And receive buffer should be set accordingly to match send buffers. Also, there is a zone sync timeout directive, and actually it is generic Nginx read-write inactivity timeout for internode communication, and it will control when to consider one of your nodes dead. So you will close TCP connection and start synchronization again. Here will be some synchronization process step by step, considering a sticky session. A new client connects, and the result of this connection, Nginx processes its request, and the result, it creates a new session in the shared memory zone. And next, this record is put into the output queue. Here, the only part that was related to cluster is that we put this record into output queue. We haven't yet sent anything to network. The model can continue with its normal operation, and as a result, this record can be updated multiple times or even deleted. We haven't yet sent anything to network, and we didn't do anything fancy. Next, the periodic sync timer triggers and zone output queue is inspected. So now the zone sync model looks what we have in output queue to synchronize. And it starts to consume the output queue until it has no buffer space available or the queue is empty. And it serializes data from the output queue and puts it into output buffer. And finally, the buffer is sent to all existing nodes. If there is an error on some particular connection, this connection is closed. And on the remote side, when a message is received, this data needs to be inserted back to the shared memory zone. And since each message has a key, So there can be three outputs. We can create a new record if no such key exists. Or we can update existing record if remote timestamp is newer. And the last output can be that we will ignore the update if our local data is newer. So we have not looked yet what happens when a number of nodes in a cluster change. It can be some really new nodes that were added to the cluster, or it can be some existing node that was disconnected previously and we established a connection with it. So when a new node is connected, it has to get full state, not just current stream of updates. What shall we do with it? Each node uses only one TCP connection, and synchronization state is attached to the connection state. It means there is no difference between nodes that were disconnected due to some networking problems previously and nodes that we just entered into cluster. Generally, it is not known whether any parts of a state were shared with this node previously or not. We are not trying to find out which part of state exists on that node. So when a connection is established, the node receives two streams of data: current updates, as described at previous slides, and a snapshot stream, which sends all existing data from local node in background. And the most recent versions of records are selected to form new joint state. And this process runs in parallel with normal operations. And at the end, all nodes arrive to the same state. And if node is not responding, current update stream can be delayed for a configured write timeout. And when a write timeout will expire, we will disconnect this node and continue with nodes that remain alive. So what we have in a wire. The Zone Sync model provides generic framing and versioning. Each message contains fixed 12-byte header, and it has a full message length, protocol version, unique model ID tag that we need to dispatch to proper modeler. Also, since we are synchronized shared memory zones and each zone has a name, it has a version and a tag, so they form a signature that must match the destination. Messages with unknown signatures are ignored. For example, you can add some new shared memory zone on one of the nodes, and of course you are not able to apply configuration on different nodes at the absolutely same time, so it's normal working situation. So such messages to non-existent zones will be just ignored. And also the data itself. Here I took a sticky model, for example, and it generates 21-byte fixed length header and up to 32 bytes of session ID. So overall, we operate with very simple binary protocol with fixed size length records, and thus it doesn't require a lot of resources to process it. A typical HTTP request requires much more processing and resources. And of course, we always want to minimize synchronized state because if state will be too big, we will get no benefit from our cluster. We will spend more resources synchronizing data than we'll have benefit from having it synchronized. So what about consistency of such type of cluster? The data become consistent eventually. There's always a time span between a value change on different nodes. The span can be reduced by tuning zone sync interval, but not eliminated. And latest key always wins. So we are depending on a proper temporal synchronization. So it is important to set up NTP or similar technology to keep your time properly on all the nodes. So consistency is ensured by the fact that each node eventually receives all objects and they are merged using a common algorithm, and finally we have same state on all nodes. And we have a key value storage, and you should remember that it's not a distributed database. For example, it's a bad idea to attempt to create same key on different nodes simultaneously. It may happen at the same millisecond, or whatever your timestamp resolution is, and different nodes will end up with different values. So some final notes. We are synchronizing objects and not synchronizing events, operation, or bytes. It is only the final state that matters that during synchronization. The history of operations is endless and it only grows with time, but we don't synchronize operations. We just synchronize whatever object we have in memory at the moment of reading it. There are some nice consequences. For example, it is impossible to overflow output queue. In the worst case, when our node is disconnected from our cluster, from other nodes, from a cluster, we will just have all objects filling our shared memory in queue, and this queue is finite. Records either arrive consistent and injected to the cluster node properly, either rejected, because the process is absolutely the same like adding local records. It actually calls the same code. And update rate doesn't affect synchronization volume. This is a typical scenario. User requests usually modify existing objects, like you start a session, the session is established, and next you perform many more requests that modify the same session. If these modifications happen within our sync interval, we don't care about these thousands of modifications. We only push the final state to the cluster. Only number of objects and frequency of reading them is important. Another consequence is that it is impossible to synchronize deleted objects because you have no objects to synchronize. So synchronized records may be created or updated. And we don't support delete operation, of course. And instead, each record has a configuration defined lifetime. It is natural for various sessions because sessions usually have a lifetime, and rate limiting models, they also usually have some notion of lifetime. And for key value store, we require that these records also have a specific lifetime. So if you really need to deal with some deleted objects, in key value store you can use some special value to mark object as deleted, but not actually deleted. So all nodes are connected with each others. And all nodes in our cluster, they are equal. There are no special nodes, just total mesh. And each node creates a stream of changed objects, receives such stream, and merges incoming objects with objects locally created. A node doesn't know whether its local values are best or latest, it just relies on them until updates from other nodes are applied. And so, of course, each node may operate locally. It doesn't make any performance penalty when node is disconnected. So, about future, probably we'll have more backends supporting synchronization. We'd like to see a better integration with DNS, maybe supporting SRV records. And of course, we are waiting for your feedback, for your use cases, what you need. And that's all. Thank you for attention. Questions?
Yeah, thanks for this great session. How do you manage the recording of a node coming up in the DNS, and if it's going down?
We're making a poll at a constant rate, just periodically making queries to DNS.
But how do you make registration of the node when it comes up? How do you add this IP address in the list?
No, this is something Nginx does not do for you.
Yeah.
Just it's suppose that you have some external mechanism for adding nodes or removing it.
Okay, got it.
Yeah. We're just looking at what we have in DNS.
Yeah. Okay, good. Thanks.
Thanks for the session. I didn't see anything about acknowledgements and retries. Is that something the nodes do?
We're using just reliable protocol, TCP. So we just push the messages to the node, and if we get in TCP error, like write timeout or connection error, we just close the connection and consider this node offline, and we start the process from start.
Hi, thank you for your session. Is there a limit on the number of nodes in a cluster?
There is no some hard-coded limit, but of course, since it's a full mesh, the more nodes you will have, at some point you will stop scaling. We've tried on Amazon with like 16 nodes, and it was still working. It actually depends on how much traffic do you have, how much data you will need to share. And
Since the controller supports close to 100 instances, so I was wondering if some testing has been done around 100 instances in a cluster.
well, again, it depends on number of changes that arrive to your nodes and how much do you need to share. So you should test it and try.
I have a follow-up question. Have you guys done any tests on AWS when you try to establish a cluster across availability zone? And if there's any special consideration that you need to do?
Sorry, can you repeat?
If you set up a cluster across availability zones or regions?
Oh, no, I was just testing in same zone. Like,
Do you have any recommendation in that case?
no. The recommendation is just to have a good connection between nodes, and maybe Amazon is not the best place for it. Okay, thank you.